working with. Computational chemistry with some indices, 400 something, 600 something. It's lecture number 15, but presentation number 2, so a lot of codes. We are in the computational chemistry course. We do want to get observables to compare with experiment, and most of our class time is invested into getting right theories, and the lab time goes into running software on hardware, right? Getting a goal to compute observables and compare with experiments. Half of semester we were dealing with Gaussian and Gaussian software, and it is enough. Today is a celebration of the last meeting with Gaussian. Next week we will start something different, but let's go over the question: how Gaussian software allows to interpret Hartree-Fock theory that we covered in class. So there will be ways how to. So each of presenters will share his or her experience on one of the aspects that can be later used in the research. Approximate time for each presentation is 7 minutes, including walking there, walking back, listening to the questions, answering to them. So if we follow the schedule, we have a chance to finish at noon. Yeah. Yes. So if you never have seen Microsoft Word and PowerPoint, which is I doubt, so that the files are labeled according to their subsequent numbers and names of presenters. So if you come here, you just select the file and click on this right little thing to put it on. And when it will be time for next speaker will be able to do the same. With this, I would like to invite to the podium Alyssa Roberts, who will tell us how to do electrostatic structure calculations with Gaussian.
So mine should be short and sweet. All right, so there's electronic structure, and then how to specify the memory and number of processes, and then how to specify spin and multiplicity. Does this not work? Oh, it does. Okay. So the first one is electronic structure. If you're in Gauss view and you're more visual, this is an easy way to do it. You open up the file in Gauss view, and then you go to the calculate tab, which is right by open file. And then there'll be a method section, and you just hit the select down menu, and those are all the different methods. They can use reviews, mechanics, and Hartree-Fock, so you can do DFT and all of that, obviously. And then the charge, spin, and multiplicity can be done through Gaussian. It can also be done through a terminal. If you're more visual, Gaussian is easier. So it's in the same tab, and then there's you can specify the spin type and the multiplicity. So this is the multiplicity here, and then this is the spin type, which is just that drop-down menu. So fairly easy. And then if you want to do it through the terminal, so you open up your file and edit it in whatever terminal you're using. And then if you want to do unrestricted, you can just put it in front of the Hartree-Fock line there, or you can not have that, whatever you want. And then it's in front of the basis set. And then we have the charge and multiplicity, which is here and here. And to change the multiplicity, you just change the number to whatever you want the multiplicity to be. So very simple. And these are the coordinates. And then if you want to specify the number of processors, if you don't specify at all in your script, then it'll designate 1 gigabyte for memory and then just 1 processor. But if you specifically want to use a certain number of processors in your script, you just type in memory equals, and then however many gigabytes you want to use, and then the number of processors shared equals whatever number of processors that you want to use. And yeah, that's it.
Okay, but thank you, Alyssa. No, stay. There will be questions.
I don't think there will be.
Can you go to the slide number 2? So in your list of methods, how does numerical expense change if you go down, down, down? Is it getting easier?
No, it's getting harder, I'm pretty sure.
How much harder?
I don't know, maybe.
What's a typical time for like your experience? How long does a single job runs?
This is like seconds or minutes, and then as you go down, it can be minutes to hours or days even. So it depends on what you're doing.
Okay. More questions to Alyssa? Who is Linda?
I have no idea. That's just.
Whom to ask if you do not have an idea?
Either probably ask Braden or Bud or.
Wrong answer.
What do you mean?
There is a person who is expected to know.
Linda handles the parallelization of Gaussian. So it allows you to run Gaussian on multiple CPU zones.
Oh, okay.
So if your job is so hard that it doesn't fit into one node, and you want to distribute over several nodes, you need to ask Russell how to use Linda.
Okay.
More questions to Alyssa? Questions 1, question 2, question 3. Let's thank her once again. So the next presenter is whoever is on the list. I think it is Braden. And so he'll continue the story about advanced use of Gaussian. So he'll show which wonders Gaussian can do for us. And there will be a little surprise at the end.
All right, so I'll be
Which side are you going to stay?
right here.
Okay, please do. That's fine.
Okay, so I'll be talking to you guys about optimization, or kind of the different things you can get from Gaussian. So you can do optimizations like single point calculations. You can calculate the normal modes. You can do population analysis. Just to name them. So you always need these keywords at the top of the input file for your geometry and chart and multiplicity. So to do single point calculation, there's no keyword specifically, you just need the basic things: methodology, your basis, charge, elements, multiplicity, coordinates. Then to do optimization, so to optimize the energy and then also optimize the geometry afterward. Each time, you just need to opt. And I often run into this problem in some situations where I need to increase the number of iterations of the electronic structure, because the default is something like 129, which is usually enough, but sometimes they bump it up to like 500 or something, which ends up working pretty well. So another thing you can do is calculate the normal modes. So you need to calculate with the keyword freak. And then something else you can do is calculating the oscillator strengths and excitation energies for the system. So this is a little more complicated, but you can do TD for time dependent. And then the default here is singlet excitations, but then you can choose the number of states you want to have incorporated into this calculation. So usually for small molecules, you can easily do something in the range of 100 or so for that. And then you can also optimize these excited states. So if you remember from PChem or something, you have, you think of your potential well and then another potential well, you optimize it, so that's called the vertical excitation. And so that's where these come from. But then you can also optimize those excited state electronic structures for the geometry by specifying the root, the excitation that you would like to optimize. So here, the default. So then I'm also in charge of telling you guys about how to create an input file by hand. Pretty easy. You have to specify your output, one of your output files, your check file. And in addition, as Alyssa said, you can also specify the number of processors and memory, depending on what system you're on. But then you have this line, which gives a list of keywords, and this P stands for increased output, so it'll just give you extra information. And so you have your methodology, optional, unrestricted, basis set, and then any additional keywords you choose to have. Then just some arbitrary title, and all of these are specified by one hard break, Gaussian license hard break. Be sure to get this correct. So then arbitrary file name, another hard break, charge multiplicity, elements, coordinates, and then about 3. I usually do like 10, but make sure you have a few hard breaks there too. Yeah, so, and it doesn't matter, you can have multiple lines as well. So to keep things looking nice, sometimes I do 2 lines and I'm constantly changing something. So here you can do multiple keywords at the same time as well. So the routine is to optimize it first and then do stuff on frequency and population analysis. So visualizing these normal modes, you can just load, after the freak calculation, you just load it into Gaussian, right click, go to results, vibrations, then it gives you the complete list of all the normal modes for that molecule. And, you can turn on these vectors, which I think is cool, and you can increase the amplitude of those vectors, and then start an animation and watch it wiggle. And you can also visualize the exact spectrum that is produced from these normal modes, or predicted spectrum. And so if you look at state 3 here, it corresponds to this red highlighted region as well, so you can pick out each one. And you can, additionally, you can save the movie in a limited number of formats, but good enough, I guess, for what you need. And then an NVO analysis, which is a little more complex, but you can kind of go into, each atom has different orbitals based upon the basis set that you do to it. You can see each, for instance, here you can see the occupancy of that orbital. So it's 0.89 electrons in that orbital. You can see it's dispersed. You shouldn't have more than 2, right? Think about it. And then you can have the energy of those orbitals. I guess that for every one. And then a different part of this output file, you can have the coefficients and, again, more percentages on it. But I don't need to go into that. It's fun. Thank you.
Questions to Braden. So questions are highly encouraged because upon something is presented here, you all are considered certified experts in this, and this can be made a part of homework or assignment or whatever. So ask if something is not clear.
How are the normal modes found? Is it from molecular mechanics or ab initio calculation?
My understanding is, well, it calculates it by taking the second derivative in polarizability. So it's kind of expensive to do on large systems as well, but it takes the energy, the potential energy. Takes derivatives over the potential energy to get.
So you get the slope, so you get your potential energy.
Exactly.
Can you get 2 slides back? So some modes give large contribution intensities, some don't. And there were several people who practiced this spectrum yesterday and saw that there are modes, but there are no intensity of spectrum. So what is responsible for intensity? Where it comes from? Thank you. Even if you do not have immediate answer, what is your intuitive expectation? Like when molecular motion responds to periodic change of electric field.
Maybe I'm not understanding.
It is spectrum. Response, ability of periodic electric field to...
Oh, are you looking for like resonance?
Yes, resonance, but what else? Some modes are in resonance with incident frequency, but there is no signal. What is the Hamiltonian of interaction between light and matter?
I'm missing this.
So, if your molecule is neutral, it will not move along the electric field, right? But you change your electric field and some motions inside the molecule start. Which property of a molecule are responsible for this response? Yes! So the molecule should be polar, or something should be polar to respond, and the different elongations of different patterns of atomic elongations will provide different change in this polarization. Therefore, they have different. Okay. More? Do you want to entertain Braden with more questions? Can we go a couple slides back? Yes. What after 0, 2 charge and multiplicity you have La symbol, right? Which element is it? Okay. What is ECP? And if you do not know what is ECP, whom to ask in this audience?
ECP.
Yes. It's a tough question. It was not in class. See on the last row, a smiling face. So it is effective core potential. For some elements, it is not immediately included into the plane running, and you need to add additional potential for exotic elements. And there are additional keywords in the input file to take it into account. So Javed will be happy to share his secret knowledge with us.
And he used the subs file for his calculations. There is some line in the below the after the coordinates.
To specify different basis sets for different elements.
Yeah, it's also include the pseudo potential.
Oh, okay, yeah.
There are 3 sections separated by star.
More questions to Braden? 1, 2, 3. Let's thank Braden once again. And next presenter is Russell Hoffman. So his presentation is of special interest. Well, everyone's presentation is of special interest, but his presentation will be very important to those of us who will do projects related to chemical reactions. From the point of view of physicists, atoms stay in the molecule, stay near equilibrium. But from point of view of chemists, during the reactions, they go way apart from the equilibrium. They go through transition states, they experience reactions, and Gaussian software has tools to take it into account. Floor is yours.
Okay. What I'm going to start with, however, is the discussion of the nomenclature of the focal basis sets, which are a little bit unusual compared to the majority of basis sets you see in Gaussian, because instead of having a series of letters that stand for words that you can read pretty clearly, these are a series of numbers that don't stand for words. So they can be between a series of 3 and 5 numbers, and the position of these digits has significance. So to the left of the hyphen, that number corresponds to the number of Gaussian functions used to describe the core basis functions. And this value, it can be usually, in the Pople functions will be 3, 4, or 6, or 7, I believe. And then the digits after the hyphen, which there can be 3 digits, or 2 digits, 3 digits, or 4 digits, all describe valence, the valence basis. So, and each of those digits refers to a linear combination of Gaussian functions used to generate that basis function. And the number of digits after here corresponds to the number of times that the valence basis set is split. So 2 refers to a double zeta basis set, 3 is a triple zeta basis set, quadruple is, or 4 is quadruple zeta, etc. In addition to numbers, we also have symbols in nomenclature for the Pople basis sets. And these symbols, the plus means diffuse functions, and the asterisk refers to polarization functions. So 1 plus refers to diffuse functions applied to all non-hydrogen atoms. 2 pluses refers to diffuse functions applied to all atoms. And then for the asterisks, again, 1 asterisk refers to polarization applied to all non-hydrogens. It means that they're applied to all hydrogens. So cases where you want to use diffuse functions for your Pople basis set, because you can add them in, would be if you have anions. Typically, those molecular orbitals are going to be larger than your standard Gaussian orbital, so you want to add a diffuse function, which will allow that to expand and treat it more appropriately. And then polarization functions you typically want to use if you have electronegative atoms where they're not really sharing their electrons proportionally. So in the Gauss view, we can set which basis set we want to use under method. So in this case, I'm using the 3-21G basis set, which you can use that without any polarization for diffuse functions. It should be known that I believe all of the smaller basis sets only allow for 1 diffuse function. And also from that nomenclature, this is a double zeta basis set with 3 functions describing the core basis functions. So then for the larger basis sets, they do change a little bit in how they're described. We can have up to 2 diffuse basis functions for the 6-311G basis set. And instead of asterisks, we now have more complicated descriptions of our polarization functions, which go from D down to 3DF. And in this list, they increase in complexity as you go down. And if you were to manually write star after your basis set, that would be interpreted as the simplest polarization function here, the DMP. Okay, so transition state searches. For simple reactions, these can be really easy, but in most cases, you're not going to get them the first try, unless you have a really good idea of what the transition state actually looks like. So in this example, I'm going to do a SN2 type reaction. And this is easy because it's well studied and we know what an SN2 transition state looks like. So if you remember your organic chemistry and the SN2 reaction mechanism, we have one atom forming a bond while the other one is breaking a bond, and we have an inversion of chirality. So that means our hydrogens are all going from pointing this way to going and pointing this way. So that means in our transition state, all of our hydrogen should be in one plane, and we should have our oxygen coming in at a bond length that is longer than its actual bonding length, and in this case, chlorine leaving at a length that's longer than that bond. And I tried this example, so I wanted to be consistent. And in that, I had my oxygen deprotonating my carbon and leaving me with like a carbene with a free chloride anion. So I tried NME instead. So in this case, my longer than average bond length is 2.5. This was kind of a lazy number. You won't always get a good result. And as you can see, I have my hydrogens and carbons all in one place. So after you set up your bond lengths, you need to set up your calculation. So for a job type, you want to select optimization plus frequency. But this will not optimize to a transition state unless you tell it specifically optimize to a transition state. You can select that. Next thing that you're probably going to want to do is calculate force constants. So in a normal optimization, it estimates a value for the Hessian, which for a transition state calculation, this is probably going to fail. If you select CalcFC, it will explicitly calculate the Hessian at the beginning of the reaction, then use those values for everything else. Much more likely to succeed, and not that much more computation intensive. You can also do calc all, and it will calculate the Hessian explicitly after every optimization cycle, which of course will take long. And this is what the input looks like. So you can see that I did one thing here that I did not put on the Gauss view, and that's I added no eigentest. And this is because the first time I ran the calculation, it failed, telling me that it expected one imaginary frequency, and it got 4. I did go no eigentest, fixes this problem, but I've read that it can also lead to less accurate solutions. Okay, so after you've ran your calculation, you can load either your log file or your fcheck file. You're going to use your checkpoint file. You need to add rec equals save normal modes to your input. So then if you go to results and vibrations, we get our vibrational modes, just like Brandon was talking about. And in our transition state search, we want to look for 2 things to verify that we've actually found our transition state. We want to see only one imaginary frequency, or one negative value for frequency, which we have here. And each one of these corresponds to an animation. And if you want to save those, just click save and save movie file. And GIF works well, but it has other. So we have only one negative frequency, that's good. And then also you need to look at what your structure actually looks like. If it's not reasonable for the reaction that you're trying to do, it's probably wrong. This is a reasonable, this looks reasonable for forming a bond here, breaking a bond here. So this is probably the correct transition state. Example of one that did not go well, this only had one negative imaginary frequency, but this is clearly not a reaction, it's just 2 molecules long next to each other.
Okay, let's thank Russell. Any questions?
So when Hartree thought, when they made their theory, initially they used atomic orbitals to make up their basis sets. You say Gaussian used Gaussian. So why did they use Gaussian instead of atomic orbitals?
So I guess I don't know exactly where the Gaussians came from. Was that from the solution for the hydrogen atom that they came up afterwards with the using Gaussian orbitals instead of trying to do atomic orbitals?
Any opposite or alternative opinions? Braden?
Atomic orbitals have cusps, so the derivatives are continuous. So it's more fun to use Gaussians. You can take infinite derivatives.
So it's a purely applied math reason. The continuous functions without discontinuities are much easier to integrate, and you always can get a reasonable answer. So it will be numerically stable. More questions?
So suppose I have a chemical reaction. I know the geometry of the initial reactant. I know the final product, but I don't know how the reaction happens. Is it possible to find the transition state?
Yes. You can do a QST2 calculation, which you give it your reactant, your optimized reactant, your optimized product, and then it will give you a guess for the transition state. And then you'll have to verify whether that is or isn't a transition state afterwards. But you can use that. I've never used IRC, so I don't know if there are ways to do it using that option.
More questions? I have one. So can you go one slide back? So if you have sequence of geometries between reactant and product, and you do want to plot potential energy surface along this reaction coordinate, where would you take these numbers? How would you parse them from log file, or what is your plan? What is your strategic scenario to get the potential potential energy surface for reaction?
I haven't done that for a transition state. I've only done that for potential energy surface scan.
But would you believe that if one looks through log file, it will record instantaneous energy, total energies at each step?
I would imagine so. That sounds convenient.
Yep.
I guess I'm confused. Why are you looking for just one negative frequency? Like, what's the purpose of that?
So that's, from what I understand, that is how you know that you're actually at a saddle point rather than elsewhere on the potential energy surface. Because your transition state can be at a
Is that for like any reaction that we model, or?
Yeah.
Oh, launch the
So-
discussion.
So to go off of Austin's, so you were stating in this one you wanted the one negative energy, but in the other one with the one negative energy it didn't work. So does that mean you need more?
Well, it means I'm probably at a saddle point, but the saddle point has nothing to do with the reaction I was looking for.
Okay, so you always are just wanting that one negative. There's never just more.
You can get more than one negative, but that means that you're not at the transition state.
Okay.
I saw one more lifted hand.
My question was kind of
Stolen.
Yeah, I was just going to be, if you have multiple, does that just mean it's a saddle point in higher dimensions?
Can answer that question.
Questions 1, question 2, question 3. But thank Russell once again. So, Vijay Shah will continue our travel into advanced use of Gaussian, and he'll cover 2 important subjects. First, what to do if we do have open shell radicals or transition metals with unpaired spins. And second, what if we do not have Gauss view on our laptops, or the connection is too slow? How to analyze Gaussian input in text format?
All right, so thank you for the introduction. So as Professor Killian said, I'm going to be talking about spin angular momentum, as well as analyzing Gaussian output without the use of Gauss view. So just a brief introduction to spin very quickly. So spin, which is more formally known as spin angular momentum, is an intrinsic property of particles in the quantum mechanical sense. So you can basically, in chemistry, one of the important parts about spin is Hund's rules. So these are just 3 rules which describe how you can find the lowest energy state in for different atoms. So for example, carbon is commonly known to have 1s2, 2s2, 2p2 due to the 6 electrons that are in its shell. So 1s2 and 2s2 are completely filled orbitals with 2 electrons each. However, for the outermost shell, 2p2, Hund's rules actually tell us that we cannot have 2 electrons in the same part of the shell. So instead of having up-down on one part of the shell, we have to have 2 ups, one on each different part of the shell. So this will give us the highest total spin, and therefore the lowest energy for carbon. There we go. So if we want to actually consider 2 particles, for example in hydrogen where we have an electron and a proton, each particle will have a spin of 1/2. So there are 4 different possibilities, noting that spin will not be commutative. So because we actually have to add the individual spins together, this gives us 2s plus 1 total multiplicity for spin, meaning that if we have spin 1, for example, there are 3 different possibilities as represented by what we call the triplet state. Whereas this final possibility, where you take the difference of the spins of the individual electron and the individual proton and take the absolute value, that will give you the multiplicity 1, also known as the singlet state. And if we apply the S squared or the SZ operators, which are represented by matrices, to an eigenfunction, for example, one of the kets in the triplet state or one of the kets in the singlet state, we can actually recover a value multiplied by that eigenfunction again. So these are just eigenvalue equations, as commonly known in mathematics. So moving on to actually analyzing the Gauss view output, Alyssa and Braden talked a little bit about spin and multiplicity in the input file, so I'm not going to go into detail there. But one important thing to note is that if you do change the multiplicity and you run unrestricted Hartree-Fock, you can still get a failed job. So for example, using this input file on the right, I actually ended up getting a failed job. However, when I increased the number of maximum cycles that Gaussian would use in order to find convergence, this job actually succeeded. This slide just shows an example of the output when your simulation succeeds. So this top picture right here shows a bunch of numbers, and then at the end you can see normal termination of Gaussian. So as soon as your simulation's done, all you have to do is open up the file and get to the bottom, and that will allow you to determine whether or not your simulation actually succeeded. And then you can also find the energy that was calculated at the end of this, at the end of the simulation using Hartree-Fock. So finally, we talk a little bit about alpha and beta orbitals in the lecture, and if you change the spin multiplicity, then you can actually end up with 2 different sets of orbitals. So if you just have multiplicity 1, or the singlet state, you're not going to end up with both alpha orbitals and beta orbitals, but rather you'll just end up with one set of orbitals where you have occupied states and unoccupied states. However, increasing the multiplicity allows for both alpha orbitals and beta orbitals, which give you different sets where each orbital can be occupied or unoccupied based on the different values of spin. So in summary, I talked a little bit about the theory of spin, and also showed that you can obtain the energy of the system if the simulation is succeeded. And it'll be talked about later about how to actually plot the density of states from the occupied and unoccupied orbitals. And then finally, you can also obtain different orbitals for each energy level if you increase the multiplicity of your spin. All right, thank you, and I'll be happy to take any questions.
Okay, well, thank you, Vijay. Any questions? Yeah.
In slide 5, you showed us one failure job. So you need more number of SCF cycle, more than 129. Is it related to your spin or anything?
So you mean like right here?
Yeah.
I guess I'm not exactly sure how to determine how many cycles you should use, but yeah, the only time that I've actually tried to use more than 129 cycles, which I believe is the default, the only time I tried to use it was when I actually got a failed job with multiplicity 2, so.
Okay. So is there have any relation with the number and multiplicity, or it's just a coincidence?
Yeah, so that I'm actually not 100% sure about.
How do you know that the failure to converge is due to the fact that you don't have enough cycles? Is that always how that is, or?
For every situation that I've encountered, that is indeed how it was. I'm not sure on an absolute scale, like if every failure would be attributed to that, but from what I found, increasing the maximum number of cycles would cause the simulation to succeed in every case.
So this might be my ignorance, but where do you go to switch how many cycles to use?
That's just right here in this line where you're actually specifying which like basis set and which method you're using. So at the end, you would just type, for example, it's actually covered, I guess, by the screen here, but it's just SCF equals, and then in parentheses, max cycles equals however many cycles you want to try.
Okay.
Yeah, so instead of like 120, instead of not having anything there, I just changed that to, I just included 500 to specify run for 500 cycles before giving up.
Okay.
Yes. Oh, yes, first.
On your first slide, just the background, I'm confused. So you have the contributions of total angular momentum. Why is the y direction like the only complex one?
That arises actually from some theory. I'm actually just going to refer you to this reference right here, but the main thing, I guess the main thing is that like each of these, like S sub x and S sub y here, the two matrices are actually generated using a linear combination of a raising and a lowering operator. So when you actually like work out the mathematics, then that's where you find the complex number for S sub y.
Okay. Does that affect like your jobs mission or anything like that?
It doesn't. No, this is just kind of something that I included to give a background on spin.
Can I add?
Yeah.
Connecting to our class material, if you have only one spin on top, your wave function is just two components, right? Two numbers. Amplitude probability for spin up, amplitude probability spin down.
Yeah.
But as always in quantum mechanics, it is complex numbers.
Right.
But if you want to interpret it as a human, we hate complex numbers. If you do linear combinations of those, according to these procedures, we can get rid of them.
Okay.
So the S sub y, it is in some sense taken imaginary part. So if you do different combinations, you get from two complex numbers, you get three real numbers.
Okay.
Okay. Once in your talk, you had results that S capital equals 2.5.
Let's see.
Further.
Okay.
Here, back.
Yeah.
Here you have S spin equals 2.5.
Okay.
How do you interpret it? What does it mean?
So that so that would just mean that like when you're adding up all of like the spins for your system, then like you would get the total spin is equal to 2.5. So like for example,
How many unpaired spins?
What's the value of spin? Of just one spin?
You mean like total spin or just like one for one particle? And
No.
I guess I'm not understanding. Yeah.
So Aaron tries to help you. So original question is how to interpret 2.5, and second question, what would be the spin, the S value if you have only one unpaired spin?
Okay, so if you have one unpaired spin, then it would just be 1/2 or 0.5.
Okay, and if you have 2.5?
If you have 2.5, then that signifies that you're either adding up like a particle that has spin 2 and spin 1.5, for example, or like you have particles with spin 1 and spin 0.5.
But you have electrons that do have spin 1/2.
Yeah.
How many unpaired electrons?
Oh, okay. That would be 5.
Yeah, okay.
Okay.
And the next presentation is by Christian Nilles, who will speak. I have forgotten what he will speak about. It was so exciting. Let's see. Observables. So he will establish a bridge from boring numbers in Gaussian to observables in wet lab.
So basically more boring numbers. Thank you, Dimitri, for the intro. As he stated, we'll be looking at the numbers we get for energies of what we see as observables. There we go. Oh. Well, I guess I'll read it for you guys. So we were going to be using the Koopman theory, which is states that the first ionization energy of the molecular system is equal to the negative of the orbital energy of the highest occupied molecular orbital. So it would be this arrow going up, and that would be our ionization. this is the band gap that will also be seen. That is between the highest of our HOMO, and then we're looking towards our LUMO. And then if we're looking at our electron affinity, we'd be looking at our LUMO up to that highest point. Also, just a side note, when I was looking up the Koopman theory last night, I found out that he has won a Nobel Peace Prize, but not in science. He was an economics person. The reason he did this was because he's a statistician at words. And so he was able to come up with this. But just an interesting side note. So just to show the molecule I used, it's the same one we've been using for all our homeworks basically, just as titanium dioxide of some sort. So after running the Hartree-Fock, which we've talked about this whole time, you go back in your Gauss view, you right-click down on your screen, and you'll pull up some your results in the summary. And then if you want to find your total energy, you look at this right here, and then this is where you'll find your total energy after running everything. Then we move forward, and then if you go and open up your file more in your Gauss or in the terminal, then you'll find all these numbers towards the bottom. And then the first one I will show you is the ionization energy, which will be this value right here. This is our top one of our occupied. And then we have our electron affinity number right here. That's the first one of our virtual energies. And then we then have our HOMO and LUMO gap, which is the difference between the last of the negatives and then the first of the positive values of all these energies. And then those are our three main things. Also, I had symmetry. I did not spend too much time, but the basic idea behind symmetry is that if you had a larger molecule, you will be able to speed up the processing by using the same symmetrics. I just looked at methane and molecule. Benzene is a better one to look at. Benzene, if you figure the whole ring is the same bond lengths all around, you can look at the one section and then go completely around the molecule and just say each one of those sections is the same value, or the same thing. You can just rerun that all 6 times. But you can go into your menu, click on edit, and then these would be the two things you'd be doing. If you click symmetricize, that just puts your molecule into a more symmetrical look. That's what I've determined. And then point groups, if you open that, and you get a larger sub-menus to look at of different ways of messing with the symmetries. And that'll be it.
Okay, well done, Christian. And let's ask him some positive questions.
Slide 5. Alpha, yeah. What does HOMO and LUMO stand for?
Huh? Oh,
HOMO, the acronym.
I missed this. You talking about? Yeah, I just
HOMO.
misspelled. It's supposed to be HOL, HOMO, the highest, and then LUMO.
Oh, yeah, but what does each one mean?
Well, the HOMO, that's the highest occupied molecular orbital, and then the LUMO stands for the lowest unoccupied molecular orbital.
So, if we define band gap, is that correct? Thing?
No, I mispicked my numbers, I guess.
Just point by your index by your finger. What is HOMO? What is LUMO?
This would be your HOMO, and this would be your LUMO.
In which units?
All of this is in atomic units.
And if you want in electron volts, how to convert?
Don't know that at the top of my head.
Multiply by 27.
Really? Is that easy?
Yeah.
Oh.
Well, point something. But
Okay.
So your gap is approximately 0.5.
Okay, yeah.
Multiply by 27, how much?
Mental math, headache.
13.
Okay.
So 13 electron volts. Is it visible, infrared, or UV?
I have no clue. I never dealt with electron volts.
Let's ask help of the club. Let's please raise hands who think that 13 electron volts is infrared. Let's raise hands who think that 13 electron volts is visible. Okay, 1. Let's lift hands who think that 13 electron volts is UV. Okay, by majority of elections, we accept that 13 electron volts is UV.
Okay, so you just base off of how big it is. IR small, visible
Yes.
a little bigger than. Okay, makes sense.
Exactly.
Electron excitation is usually in the UV visual.
Yeah, so I guess it'd be the same if you were using one instrument.
I'm not sure if you know the answer, but why is it like in columns or like in rows like that? No, not in rows, but why is it in columns? Like what is the difference as it goes along?
Well, I mean, it's just the way the program goes. I mean, you just follow it that way, and then it goes back down the next one, like you're reading a book.
Okay.
More questions?
In Austin's thing, when you're coming up, you can type up a certain sequence of commands. They put it in straight column form. But that's Austin's presentation. Go forward.
What does letter G on your head mean?
Huh? Oh,
You have-
G. Green Bay Packers.
So it is not Gators. You didn't
No.
get converted to their
No.
for them.
Nope.
Okay, let's thank Christian once again. And next presentation is by Austin Breuer, and he will present again, as each of you, very, very important subject. So how to interpret results of electronic structure calculation in case the amount of energies is huge. So previous speaker, Christian, told how to pick up just couple of energies of molecular orbitals and connect them with reality. Ionization, affinity. Austin will tell what to do if there are too many of those.
Yeah, thanks for the introduction. So yeah, I'll be covering what that is, just the density of states, how to actually interpret it, and then also how to visualize it from Gaussian and Gauss software. So just kind of giving a file background, just so no one's confused as I'm going through. I use this titanium hydroxide. I call it a polymer, but Dimitri definitely did correct me. It's more of an oligomer. So I just use the file name of poly, but it's definitely more of an oligomer. And then I just obtained all the normal processes, basically getting us up to the point that Christian was just talking about by creating .com files using Hartree-Fock methods, and then actually obtaining what I was looking for is this ti-poly.out file. And that out file is what kind of allows us to actually understand or actually start to plot those density of state functions. So this is also just some equations that Dimitri added. This is I'm not going to say I added this. So this is just helping us kind of understand where I believe those values were coming from, just getting us up to this initial point. If you have anything else to add, please let me know.
Wait.
Yeah.
What are the symbols at the bottom row? Epsilon 1, epsilon 2?
Well, those are going to be the different energy levels, correct? Or right?
Of orbitals. Same that Christian was showing.
Right,
8
but
minutes ago.
we're just going to have it for a much larger expanse, so then we can model this the density of states. Is that accurate? Okay, perfect. So then I also needed to talk about curl scripts as well, and this is what kind of answering Alyssa's question we were getting at with creating these instead of just kind of large files of information that kind of has energy everywhere in these nice kind of organized columns. As long as no one's colorblind in this room, I really don't think I need to kind of go over too much of what all the code means, but really what that, the kind of important things here, what it comes down to is just these two columns of energies, and those energies will be just associated with differences in them. And then I didn't include all of, it's a huge file and a huge column that comes out. But if you keep going down with this file, that 2 turns into a 0, and that's just the differences between the HOMO and LUMO gap, which you'll be able to see in the next slide when they're actually illustrated as well. All right, and then this is how you were actually plot and visualize this information or this difference in energy. That's the new plot software. Again, just kind of refreshing for the class on how to actually do that. You can follow that code right there just to kind of actually get the figures out of it, edit them as you want, etc. And this is just a good example of a little experimentation that I was doing last night. The figure 1 just shows a line width, a very small line width, so you can see that it's just it's impossible to read really without zooming in on it to an amount that I wouldn't like to do. Whereas in figure 2, I used a line width of 0.1, and you can start to see, first of all, the band gap is super clear. I mean, it was kind of in both, but then you can also see the differences in the valence band, and then also the conduction band as well. So yeah, that's kind of what you can do to just parameterize the data and get more information out of it. So this is, I think this one actually I can go back to that one and explain it more, but I actually like showing this one a little better too, just because it shows kind of that band gap that we're looking for. And if we go back here to these previous slides and how we're actually understanding these figures, this is the band gap and the Fermi level that's between them, and just the different HOMO and LUMO areas that these energies are associated with that specific oligomer. This is just kind of more visual representation or graphical representation, showing you just again where the conduction and valence band is. So kind of just a repeat of the same information. And I like this one to explain it more, just because it kind of shows the different energy levels associated with the conduction band and valence band with plotting it. So really what it comes down to then is just showing you guys how this data and density of states, or those energies that we obtain from the Hartree-Fock calculations, can be visualized and actually presented in graphical formation, and also the column representation, which just makes it easier for us as computational chemists to deal with. Really comes down to that's just a significant tool for density of state modeling. And then if you just go back to the file that I was using for this whole thing, going back to this kind of demonstration, you can see this large band gap that we have with this titanium oligomer, which ends up being more of an insulator type molecule. So.
Okay, let's thank question.
So where's the cutoff between a semiconductor and an insulator? There is a band gap, but is there a certain value where we stop saying semiconductor into insulator?
Yeah, that's a good question. As far as I could tell, it would really just be as it gets closer and closer to almost that overlap. And I know semiconductors aren't overlapping, but I would say it's just, I'm sure there's some kind of value out there where, this is saying it's semiconductor, but I'm sure it's also just a little bit of observation as well, and how it acts physically too.
Can I add?
Yeah.
Related to question to you. If the gap belongs to UV, insulator. If it is optical, semiconductor.
Okay.
Infrared, it's more close to metal.
Okay.
Very roughly.
Makes sense.
In the next figure, this figure is not here.
This one?
Yeah, you showed that in conduction band is very discrete number, it's small line, and valence band is big line. What is the significance of this presentation?
I think
just
yeah. So I don't think.
Can I add before you start?
Sure. But
Probably, Jabat, if you or any of us do not see on this gray background the color coding of this picture, where the arrow of conduction band shows field area there. So it is not individual levels, but field areas. Okay, please go forward answering if Jabat still has the question.
Sure, and I mean, kind of how I interpret it too is that I think you're just looking at this band part. The conduction band would just continue into higher energy levels. It's not just a singular line or anything. I think that might be a little misrepresented in the picture, but.
I mean, that shade indicating that is occupied orbital, is that, or?
Well, that should be the occupied C. That's the HOMO. Right.
Okay, I have another question actually on slide 4. And you showed us one equation. What is this equation do?
This equation?
What is this?
So this is, sorry. This is the density of states equation, or yeah, density of states equation. And this just compares all the energies that are associated with the energy transitions or the differences between the band gaps, and doesn't take them, correct me if I'm wrong, but it doesn't take them as discrete values, but it takes them as continuous values.
Then it arises another question. What is this two E? You show two energy. What is this two energy?
The two energy differences are between,
energy and this energy.
yeah, the two energy differences are between the ionization energies and I believe the electron affinities that we were pulling from Christian's data as well. I could be. Yeah. It had it included on the thing too. I probably should have included it, but I don't honestly remember.
More questions to Weston? If not, thank you once again. So, next presentation is my favorite subject. So, it will be presented by Landon Johnson, and my favorite subject is how to plot orbitals. So, independent of whether you got discoveries or not quite in your work, if you show nice orbitals, everyone will like whatever you explain. So orbitals are critical for artistic and aesthetic evaluation of your research.
Yeah. All right. So the first thing that you need to do when you're going to try to plot some orbitals is you need to format your checkpoint file. So the whole purpose of a checkpoint file is just it's machine readable essentially, so it's not humanly readable. And so for use as like an import or as an input file, it doesn't really work so well. So that's the whole point of doing the fcheck. So when you're running this command, if you don't specify an output file name, it'll just take the same name and just put fcheck on the end of it. If you want to give it some other file name, you can do that. You just need to actually specify what it is. I forgot enough there, so that was a bad one. So the next thing that you need to do is you need to figure out which molecular orbital it is that you're trying to plot. So to do that, you want to look in your output file, not the fcheck or the check file. So when you're doing that, you can just do like the more command and scroll through for a while, and you'll eventually find your energies. Much quicker way to do it, I guess, if you don't use the Perl things, is just use the grep command. So you just do grep whatever it is that you're searching for in quotes, and then the file that you're searching for it in. It'll just pull all this right up for you. So that's just a lot quicker. And then, yeah, we already talked about how to figure out which one is a HOMO and LUMO from that. So once you figure out which molecular orbital you want to plot, then you have to generate a cube file. And so the cube files just have the volumetric data stored in them. And from that, then you can actually plot your molecular orbital. So this is the command that you want to run here. Don't do what I did and forget an O, because then it will fail and abort. So make sure that you remember that. And when you're doing this, you specify which molecular orbital right here. So you can replace that with AMO equals whatever, or BMO equals whatever for alpha or beta orbitals, respectively. All right. So now that you have your cube file and the data that you need, you can open up your file in Gauss view so you can actually plot something. So you just want to open it up with the usual Gaussian command, or however you want to do it. Go into your results window, surfaces and contours. That'll open up this window. From there, you just want to set your ISO value to whatever it is that you want to do. A smaller value will basically blow this up, and then a larger value will kind of shrink it down, because this is basically telling you the density of electrons that you're looking for. So like a higher density of electrons is only going to happen closer to the atoms usually. So then surface actions hit new surface, and it will plot your isosurfaces. So if you have an open shell configuration, the usual Hartree-Fock method will fail when you try to do your calculation. I use the wrong file on that, whatever. So instead of just doing the regular Hartree. I was in a hurry and not paying that much attention, I guess. It should be HF, and it shouldn't be going for geometry. It should go for energy. So all that you need to do is just add a U to the front of it.
So you were not using these files for actual calculations?
No, I just was just typing stuff up. It's just like, okay, copy paste, copy paste. And I guess to keep beating the dead horse, you can change your charge and multiplicity in your file there, and that'll give you different results. And that's it.
Okay, let's thank Landon. Anything you wanted to ask about plotting orbitals?
Not about plotting, but is a molecular orbital an observable?
No.
So you couldn't take a picture of a molecular orbital?
No, you could figure out where the electron is at a specific. You make an observation of where the electron is, and then the electron will be in that particular spot. But the molecular orbital basically tells you where you're likely to find it if you were to try to take that picture. Yes.
So what's the importance of the O?
I am not entirely sure, actually. I tried to look into that briefly, and in the syntax there is a spot here, but usually it's a number that goes there. So I'm not exactly sure what the actual point of this
Can we
is.
interpret the letter O as orbital?
That's kind of what I figured, but I don't know, it just seems...
Let's keep alert to the next presentation when the letter O will be replaced by something else. And you can see the trend. More questions to Landon? If no, let's thank him once again. And last but not least, Daniel Ramirez will give us a way to interpret results of Hartree-Fock calculations for the sake of synthetic chemistry and interpretation of reactive properties of molecules. So he will tell a little bit more about integrated characteristics of electronic structure. Instead of individual orbitals, he will tell about overall charge distribution and potentials, and will try to connect it to ability of molecule to participate in chemical reactions. For Christian, we should stay alert and look for keywords, because he will be also using CubeGen command. Okay, floor is yours.
Thank you for the introduction. Mentioning pretty much everything we just talked about. In short, so with the molecules I used, we pretty much used the Hartree-Fock approximations to be able to solve out the time independent Schrodinger equation. And I guess I didn't really include the Hartree-Fock equation, how it's solved. Guess I could show that later whenever I find out how to work out the pen on the board. But the first thing I'll talk about is Mulliken charge analysis. This, you don't have to add any special type of keyword or anything to it. It is automatically in the output file whenever you're done running your job. So I'll be able to find out how this is. You just go to results, charge distribution. You already can see the word Mulliken up there. And we're doing this, we'll turn your, well, after you hit the color atoms by charge, you'll be able to see more so where the charges are going on. So in this picture real quick, this is from our homework assignment that we had the other day of the titanium 5 oligomer. Here we see the transitional metals, the titaniums, having a green charge. The green charge is indicated a positive charge, and looking at the periodic table, you can assume that transitional metals such as titanium will have a tendency of having positive charge, while we have the more darker red colors having a negative charge, which is pretty much also, if you have any kind of periodic table knowledge, you can assume that oxygens have a tendency to have a negative charge because they're electronegative. So the hydrogens are here have a kind of a darker greenish, so they're not really too positive, but they're more closer to positive than negative. I guess that's kind of synonymous with oxygen kind of taking apart most of the charge that that hydrogen has. But in case you are colorblind, we do have a colorblind student in the class. There is an output file, so you can see it. Also, I guess referred back to that, you could also change the color scheme to a more friendly grayscale as well. I didn't get a chance to figure that out, so I apologize. But the output file does have the charges in numerical form if you are a quantitative person, and referring also back to whenever you put your initial input file, how overall charge. So I ran this one with having it saying that it has 0 charge. So some should equal up to 0. So say if you did have a -1 charge started off, your sum should end up equal to -1, and in theory the rest of these numbers also move around. So correspondence to that. Isosurfaces. So one of the first things I was asked to figure out was electron density. So basically, electron density is the probability of the particle being between two, I guess, areas, distances. So, and this is usually just given by the integral of a product of the wave function. So, back to, I guess, what we do after the 0, do a cube gen 0 density. So this will give us a cube file that shows basically a density. Pictures right there. If you if you want the visual aid of it, just go right there, surface actions, put map surface. Oh yeah, here's also another quick way. If you happen to forget the keywords, there's a way you could cheat using the Gaussian client. Just go to cube actions, make a new cube, and then you'll get all these beautiful options. So in case you forget keywords, like you remember the other day we had a homework assignment with the alpha and beta densities. Yeah, there they were too. But more on that. So whenever we click up the map surface, we get a little, I call this the caterpillar. From you remember whenever in grade school we had that little book to read. So this isn't really too readable. So I found a way how to play around with it. Oh yeah, so basically what you do is just go right here, display format. I like white backgrounds because it's kind of easier to tell than the ugly blue color they give us, or purple, whatever it is. And then you just go to hit the top right surface option, go to transparent, move that all the way to the right. Then we get a much more easier visual aid to tell us where it is. So basically we have main colors to look at is the blue areas, the yellow and red areas. This shows us more so where the density of our electrons should be. It makes sense that most of our electrons are in the middle, where more of the so-called electronegative atoms are at. They reside at where they have more of a pull. And you see some blue areas. It's kind of hard with this picture. I couldn't find a general area with it, but if you move it around, you see a sort of bluish area around the two titaniums, which I guess that means that there's a positive charge there between those, so there's not really that much electronic energy in that area. But that's pretty much it. You can tell it right there. The color scheme up there, you can change that as well in case you wanted a more visual aid for grayscale users. The other thing I had to do was find out the electrostatic potential maps, and in this equation, the K is just a constant, with the Q's being a charge divided over the distances between these two electrons. So basically right here, after the Q gen 0, to figure out potential, if you want to rather work from the terminal, potential off the formatted check file, your file name right there, I just put ESP because it's easier to find out. So purposes of finding electrostatic potential, let's find the reactive side of a molecule, and you'll be able to see this more in depth in picture in a couple seconds. So right here we have, you remember when I was talking about where more of the electron, so-called electron density is at? You see it once again more in the middle than around the sides where the hydrogens reside at. Well, the OHs on the side fragments reside. Here we see, I like to call these the hot zones because they look kind of brighter compared to the rest of the area. The only thing that I thought was a little funny was the holes around here. There's a big old, I guess in the case of my back equation where I mentioned that more reactive sites it is, may or may not have a high reactivity in that area compared to more of the inner molecule or so the hot zones. And see the scale right there, the energies that has or more so the spot where it'll react to more for reaction sites. If you remember, go back to organic chemistry where these would be more plausible sites that will be attacked from with nucleophilic attractions and all that fun stuff that organic chemistry had offered. And that's about it. I'll open up the board for any discussion or questions.
Okay, let's thank Daniel and follow his suggestion on opening the discussion. Can you scroll to very beginning, maybe second or third slide, with Mulliken numbers? Yes, here. So you do have on titanium the charge is about +2 and the oxygen about -1. But through chemical intuition, it should be +4 and -2. So why does it differ from chemical intuition expectations? Is it regular or should we multiply it by factor? Just your own vision. It's not a like exam question. It's just your strategic plan of.
The fact that whenever I looked at the map and I saw some blue in between the two titaniums, I just figured there was some type of sharing going on between those two. I guess they take some of the load off. Is what I figured on it because I just really couldn't explain why I saw some blue in between the two titaniums. Whenever they were well, like yes, right here, there's that blue. If I moved it around, I could see I was able to see sometimes a better visual of there being more of a blue area in between it.
So you're telling that there are areas in between atoms where the atomic orbitals overlap and it is hard to assign charge?
Yeah.
Okay. So it is more qualitative rather than quantitative too. Okay. More questions to Daniel?
Is there any better method than Mulliken charge?
I figured that there should be, just because since Mulliken charge is already pretty much given to you without any extra keywords, it's kind of a pretty good approximation to be able to, I guess, put you into the right track of where you should be thinking about. But
you should ask him, since you're asking, you probably have something in mind. Ask him back.
I know he does. He has a big old smile on his face when I'm talking. So I guess you have a better way of doing this?
Maybe MBO would be better than Mulliken charge.
MBOs?
More questions? Let's go to your further. Stop here. So how do you interpret this bright areas around oxygens?
As those oxygens be pretty highly reactive, I guess. That's where potential should be lying.
Deeper. The depth of potential near the oxidizing elements should be much deeper compared to others. And if you have seen research work by Landon, where he has, and by Aaron, they have shapes with very deep potentials near iodines or oxygens, right? Mm. So it is the same thing, but in 3 dimensions. More questions to Daniel? If no, let's thank him once again. So, where are we? So, let's thank all the speakers for making an excellent presentations. So from now on, there is a hope that by listening to experts in one areas, we kind of make an average temperature over the hospital. So everyone gets the same level of knowledge in all areas, right? And we are not going to use Gaussian anymore in our lab sections, but very soon we will start research projects, and all these skills can be very useful towards completion of research projects. So let's thank all speakers and participants of the discussion once again. And the meeting is dismissed. See you on Tuesday in class for next didactic lecture.